start. So it's, we always say it's my great pleasure, but with Curtis, it is truly my great pleasure. And the reason is that Curtis is my student, and he's completed his PhD in 2017, and he worked on this a tool called MathCheck, which is a combination of computer algebra systems and SAT solvers aimed at solving mathematical problems. Subsequent to that, Curtis was a postdoc in my group for a couple of years. And then he did a postdoc with Kevin Chung and Brett Stevens at Carleton, following which now he's a professor at the University of Windsor. And I call him Kurt High, so it's like the plural of Curtis because he's so productive. So without further ado, Kurt High, please take away.
Oh, thank you, Vijay, for the gracious introduction. And I'd like to particularly thank the organizers for running this great workshop and giving me this, it's my honor to present my research on computer algebra and SAT and for how we can apply them to solve math problems. All right, so let me start with motivation. So we all know that mathematicians are utterly fascinated with searching for structures, particularly ones which satisfy really elegant properties. All right, so I have two quick examples on the slide here. On the left, I have a graph, and I've colored the edges of the graph so that every vertex is adjacent to exactly one edge of each color. On the right, I have a chessboard, and I put a queen in every square. Right, and I've colored the queens so that queens which could attack each other are colored differently. Right, this just means every row, column, and diagonal of the board is colored differently. Right, and so you can imagine either coming up with some kind of mathematical, theoretical way of constructing these things, or writing a computer program which would perform a search and look for such colorings. A third example, which is near and dear to my heart, is Hadamard matrices. This is also a very a mathematical object which is defined really elegantly. So we have a square matrix, and all the entries are either plus or minus 1. And the defining property is that any two rows of the matrix should be orthogonal to each other. Right, so they're mutually orthogonal. This is a very restrictive condition, and scientists have studied these things for over 100 years. They've used them in statistics and coding theory to, for example, when they were communicating with probes being sent to Mars, you want to encode the data sent in some kind of error-correcting fashion. One way to do that is to use the rows of your Hadamard matrix to form the code words, right? And then this orthogonality property is saying that two code words are kind of maximally distinct, right? So it has good error-correcting properties. In any sense, these things are really interesting from just a theoretical standpoint, and mathematicians have studied them for a long time and trying to construct them in as many orders as possible. One mathematician who did this was John Williamson in 1944, and he actually found the example shown on this slide here. So this is an 8x8 Hadamard matrix, but he actually went further. This was an amazing paper. He found many different examples of Hadamard matrices. Here's another one. This is a 16x16, and it's formed, you can kind of see how its construction works. It's formed by submatrices known as Williamson matrices. In this case, they're order 4, and you put them together in this nice pattern, and you get something which is Hadamard. Now, remember, he did this without computers. So it was a very impressive paper because he actually went up to, here's a order 8 Williamson matrices, order 16, and believe it or not, using order 32 Williamson matrices, he got up to 128 by 128. Right, so this is an amazing piece of work because he did it all by hand. Right, he proved theorems about them, and he used those theorems and then some kind of trial and error process to find these examples. Now, the interesting thing was, he got them up to 2 to the 5, all the powers of 2 up to 32. And then he says, well, it would be nice to know whether these things were in some general, there's a general theorem. Does this pattern always extend? This would be nice to do. He couldn't, the computations become too involved. He was only able to give these explicit examples. He gave some other examples, but he didn't have a general theorem. Actually, this was an open problem from 1944 up to a few years ago. It was not even known if there was a Williamson matrix of order 64 until we ran searches for Williamson matrices. We actually ran exhaustive searches up to order 70 in all even orders, right? The searches found many examples of Williamson matrices, and in fact, many examples in order 64. we examined the patterns which were in those matrices and actually extended it, right? They go to all powers of 2. So now we actually have a general theorem which says Williamson matrices do exist in all powers of 2. So the moral of this story is sometimes you really want these computational searches, right? It's great when you can come up with some kind of theoretical construction, but that's not always possible, or it's very hard to do, right? But when you get these, all these exhaustive searches via computational means, you're able to examine the data and then sometimes actually prove, a general construction. So to give you a sense of the state of the art previous to this, there's 2 fields which had been used to search for Williamson matrices. One was SAT solving and one was computer algebra. Computer algebra, the state of the art in 2006, was to search for Williamson matrices up to order 22. And then in 2016, the state of the art using a SAT approach was to search for Williamson matrices up to order 30. All right, so remember, we got up to order 70. So this really demands an explanation, right? You might be thinking, well, okay, this is pretty good. It's more than double the order. But remember, this is an exponentially size growing search space, right? Order 70, the search space in order 70 is over 25 orders of magnitude larger than the search space in order 30, right? So this is not just slightly faster. This is astronomically faster. It's like you would think it would be impossible to exhaustively search a search space of this magnitude, but indeed it actually is feasible. And so my goal for the rest of this talk is to give you an intuition why it's able to get up to, why we're able to search such enormous search spaces. So I don't have to spend too much time on SAT. I assume most of the people in the workshop are familiar with this, right? This is the classic satisfiability problem from logic, and SAT solvers are very effective at finding solutions to the SAT problem, right? So some of the things they're used for, they extend far, the applications extend far beyond logic. They're used for hardware and software verification. They're used for solving math problems. For example, Marion has lots of results in this line. On the right here, this is a coloring of the integers from 1 to 160, subject to the constraint that a and b and a plus b are never colored the same. Now, the interesting thing is this does actually not extend to 161. 160 is the maximum number of integers that you can color using 5 colors. And so this is what Marion showed with a SAT solver, that it's impossible to go to 161. Right? And so you can use, the SAT solver also provides unsatisfiability certificates when something is unsatisfiable. And so this is also a very important property of SAT solving. Now, SAT solvers are great when they work well, but sometimes they also will fail. And this is also very well known, right? And embarrassingly, sometimes they'll actually fail on totally trivial problems. The classic example of this is the pigeonhole principle, right? So imagine you have 20 pigeons and you have 19 holes. And you want to find a way to put the pigeons into the holes. Every hole is only large enough to contain 1 pigeon. Well, obviously this is impossible, right? There's no computation that has to be done here besides just counting the pigeons in the holes. But a mathematician can obviously see this, but a SAT solver, remember, when you're translating a problem into SAT, you lose the context. The SAT solver doesn't see pigeons in holes, it's just these trues and falses, right? And it only makes the most basic logical inferences. It doesn't think at a high level the way a mathematician thinks. So in fact, it'll actually take exponential time on this problem, basically trying to put every pigeon in every hole. Which brings me to the computer algebra system. All right, this was my background before I started working in SAT. And you can think of a computer algebra system, or at least I think of it as executing mathematics on a computer. Right? It allows you to work with mathematical objects at a very high level, kind of the way a mathematician does. So an example of this would be you give it a matrix, you can compute the row reduction. You can compute the closed form solution of integrals or sums or transforms. You can compute with symmetries and groups. Another example on the slide here is you give it 2 separate graphs. These are 8 vertices, and each vertex has degree 3. And the question is, are they isomorphic? Are they actually the same graph in disguise? And in this case, you give it to a cast like Maple, it'll actually come back with not just the answer, it'll tell you if they are isomorphic, explicit permutation of the vertices, which will make the graphs the same, right? So I've actually color-coded some edges here to show you the structure and reveal that, yes, these are the same graphs. Okay, so CASs are great as well, but from my perspective, in my research, they're not so great at doing this sort of exponential size search space. For example, in the Williamson example, when you have like a huge space that you want to look through. But if you think back to a SAT solver, what the SAT solver is doing is inherently a search problem, right? It's trying to find that needle in the haystack. Maybe there's only one satisfying assignment of your formula, right? And you're tasked with trying to find it, right? You're trying to find that needle in this exponentially large sized haystack. So if SAT solvers are good at anything, they must be good at the search problem, right? They're built to cope with that immenseness, whereas in a way that CASs typically aren't. So when you say it like this is a very natural paradigm, right? In hindsight, SAT solvers are really great at search, CASs are really great at math, and there's lots of mathematical problems where you want the power of both, right? You want fast search and you want expressive mathematics. Surprisingly, this was, both of these two fields were very well developed, going back to the beginning of computer science. It's kind of surprising that it's not only until relatively recently that these fields started interacting with each other. All right, so it was noticed in 2015 by Erica Abraham and others that these two fields really have much to learn from each other, right? And they organized a workshop, the first one being at Digital in 2015, and they, since then, this has been like a budding new field of research. There's been associates of this SC² project in over 40 universities and 15 companies. So people are really starting to take notice and using the techniques of both fields to solve problems that couldn't otherwise be solved with using just the techniques of one field. This is also where I entered the picture. Like EJ said, I was doing a PhD at Waterloo, and we started working with MathCheck. It was actually independently. We devised this first SAT plus CAS system that we called MathCheck. And so we use MathCheck, as I mentioned, to search for Hadamard matrices. This was one of our first applications. And you can see on the right here, this is one of the 100,000 Hadamard matrices that we found. This is actually a cross stitch of a Hadamard matrix designed actually by my partner. It's sort of really nice to be able to put your research into like this nice visual form, right? So it's a nice way to actually see the matrix. In any case, this was only one of 100,000, right? So we were like really excited that, we were even at the first one, and then we just kept finding them. So, and I'm happy to report the work we did on Land's problem recently won a Best Paper Award last year. And so I wanted to talk for the rest of the talk, mostly focused on Land's problem, right? But I just do want to mention we did solve many different problems from many different domains of mathematics shown on the slide here. So if you're interested, I'm happy to take any questions, or you can check out our other papers. Now, just give me a couple minutes to talk about the history of Land's problem, because it has a very interesting history, right? Dating back all the way to Euclid in 300 BC. So Euclid did something interesting, right? He was the deviser of the axioms of geometry. He wanted to put it on a sound foundation, and he devised 5 axioms, which he said characterize all geometric truths. The interesting thing was 4 of the axioms were totally simple. The 5th axiom, known as the parallel postulate, was much more complicated. Everyone agreed that it was definitely true, but some people were unsettled by it was so much more complicated than the simpler axioms, right? They wanted to prove this parallel postulate in terms of the simpler axioms. They tried to do this for 2,000 years, and they consistently failed. And there was a reason why. The reason was noticed in the 1800s, starting with the work of Gauss and others. There are alternative models of geometry where the parallel postulate will not hold, it will be false. So let me give you one slide of summary of what these geometries would look like. So imagine you have your Euclidean plane and you stick it on the ground, right? And you're standing out and you're looking at parallel lines. And you look at them, they go off to the horizon. It looks as if they meet on the horizon, right? Like train tracks. Now the horizon is not actually a line, so they don't actually meet, but imagine you just added in the horizon as a line into this plane. And once you make that intuitive leap, you realize now you have a new model of geometry where parallel lines don't exist. And this is what's known as a projective plane. And interestingly, despite this immense amount of study, there's still open questions about projective planes. We don't even know all the projective planes which exist. if there's only a finite number of points. So what would this mean, right? What's a finite projective plane? I've given you a couple of examples on the slide here. It's nice because you can just draw them out, and they're nice and colorful drawings here. You might be looking at them and saying, okay, well, wait a minute, this doesn't look like any geometry I've ever seen, right? First of all, you're saying this purple circle is a line, and yes, it is a line based on the definition of a line, right? The definition is given above, right? Line is a set of lines and points satisfy these axioms, and this is going to be our definition. The main axiom here is if you take any two lines, they meet at a unique point, right? One and only one point. And then an order is going to be one greater than the number of points on the line. Okay, so why do I bring this up? Because people have studied these things for hundreds of years, and they have not yet succeeded in classifying for what orders projective planes exist. We know the answer up to 10. So they don't exist in order 6. This can be ruled out mathematically by a theoretical obstruction. They exist in every other order, so you can just give a construction. Now 10 is the very interesting case. This is Lamb's problem. Nobody knows a projective plane of order 10, and yet nobody knows any theoretical reason why one shouldn't exist. So you could conjecture either way. Indeed, people had conjectured either way. Either it exists, some people thought it existed, some people thought it didn't. It's named after Clement Lamb, who was a mathematician at Concordia University in Montreal, in honor of him because he extensively studied this problem in the 1980s for a complete decade, essentially. In the end, with a team of programmers, they were able to resolve the problem. They actually got a lot of press for it because this was, like I said, a centuries-old problem, and they solved it in the negative. They ran a computer search for months on the most powerful supercomputer of the era. It was a Cray 1. They did not find the projective plane. So this was a proof that it didn't exist, but the proof is, in quotation marks. Some people were kind of unsettled by it because, it was using custom-written software run a single time on a single piece of hardware. And at the end of the day, there's nothing to check. How do we know that the computations were successful? You don't. You just have to trust them, right? Maybe there was a hardware glitch or a computer, there was a bug in the software, or there was an administrative error. All these things are actually not that unlikely, right? This was a very hard computation to do. And so some mathematicians thought, they really dreamt of something more verifiable, something that could be certified by an independent party. This is where we come in. We actually gave the first verifiable proof of Lamb's problem. We did this, as I will describe, using reduction to SAT, and then use what's known as the cube and conquer method to solve the SAT instances. So this is a method pioneered by Marine and Oliver Kuhlman and other collaborators. And it's an amazing method when it works. You can look at their talks on it. I'll just say what it does is you take this huge SAT instance and you split it up into like bite-sized chunks. Right? This has two main benefits. One is that you can fire it off on a cluster using parallelization. Each of the sub chunks are independent and of approximately equal difficulty. And second, it actually works extremely well with SAT solvers. SAT solvers perform much better on these bite-sized chunks than they do on just one large problem. So you actually get a super linear time speed up if everything works correctly. Okay, so cube and conquer is not enough on its own to solve the problem because, as I mentioned, SAT solvers do not know the mathematics behind the problem. People had studied the projective plane of order 10 for for centuries, and they come up with a lot of theorems about it, properties that it must satisfy, and we would want to exploit these theorems in our search, right? And so let me give you first just a quick summary of how we can do the encoding, right? How you're going to code this on a Boolean logic formula. So it's actually not too bad. Obviously we don't use these nice colorful diagrams. We're going to use what's known as an incidence matrix. So you take your lines of the plane, you're going to make them rows of this incidence matrix. You take your points of the plane, you make them columns of the matrix. And then if you take the ith line, and if it contains the jth point, you put a 1 in the ijth entry here. Otherwise, it'll be a 0. So in SAT context, you just you have a variable for every entry in the matrix, and the variable is going to be true if that entry is a 1, the variable is going to be false is the entry is a 0, right? So you just define a bunch of variables. And then you come up with a conjunctive normal form encoding of the axioms of a projective plane. It's actually not too difficult. I won't get into all the details because I want to focus on the SAT plus CAS method, right? What can we use the CAS for? And there's many things. One of the, first of all, how does the SAT solver work? Well, it's doing like finding partial solutions, right? It's going to assign some variables to true, some variables to false, some variables are going to be left undefined. And then it finds solutions which satisfy the constraints up to some point, right? An example here on the slide, I've given you a 4-point and 6-line partial projective plane. All right, so when you find this partial solution, you give it to the CAS. The CAS can then analyze it using the theorems that it knows about the projective plane, right? In some cases, you can just eliminate the solution, or you can do is you can analyze it and then shrink the search space further. A classic example of this is you analyze the symmetries of the partial structure that you found. In this case, look at it and rotate it 180 degrees. If you rotate it 180 degrees, you get something which looks the same. That means you can block it, right? They're isomorphic. There's no sense in searching the space defined by the second example because it's going to be the same as the space defined by the first example, right? So we can block the second and go on the rest of the search. Why is this? This is important because every single time you find a new symmetry, you can shrink the search space further. And in some cases, there's lots of symmetries that exist, right? So this is just one way you can use the CAS and to dramatically decrease the amount of computation that you're doing. So in summary, you can split up the space into 3 main cases. This is based on mathematics known in the 70s. And each case gets progressively more difficult. So in the first case, there was a SAT approach that solved the first case. It took around 5 minutes. There were several different CAS approaches by different teams. Over the years, they ran between 3 and 55 minutes, depending on the CAS and the implementation. We did a SAT plus CAS implementation, and we got it done in 7 seconds. Right? So it was by far the fastest. Plus, we got a certificate at the end that can be verified. Right? The second case, previously, the last solution took 16,000 hours. This was on a desktop machine or a cluster of desktops. We did it in 30 hours. Right? So the SAT plus CAS was exceptionally effective in that case because there was lots of symmetries in this case. Right? There was over 1,000 symmetries. This gives us a huge speed up when we remove them. The third case was the hardest. It took around 2 years altogether, but less than a day in real time because we farmed it out to a machine with 1,000 processors. The proof is quite large. The certificate was about over 100 terabytes. This is in compressed DRAT format. But it can be checked, and we formally verified it with a formally verified proof checker. So I mentioned there's a lot of trust necessary that goes into, for example, the previous searches, like Lamb's original search. There was also an independent verification of Lamb's search done a decade ago in 2011. We actually found discrepancies with both of these searches, not only the original, also in the independent verification. By discrepancies, I mean they asserted the existence of partial projective planes, or the non-existence of partial projective planes, which actually we found do exist. I've shown one on the right here. This is a 51-point partial projective plane, which was explicitly asserted not to exist in the 2011 verification, and we found it, right? So there must have been a bug in the previous search. We don't have access to their source code, but we know it must be buggy because they didn't find this partial solution, which they should have found. Although our final results did correspond, we did not find the projective plane of order 10. Okay, so coming back to my promise at the beginning of the talk, how did we, and the Williamson example, how did we get up to order 70? Right, and this is basically to demonstrate how you can use the CAS in many different ways, right? It's not just about symmetries. And this is one of the beauties of the method, is that the CAS has a huge storehouse of mathematical knowledge, right? You can use many different functions in the CAS in many different ways. One of them is based on the Fourier transform in this case. So remember when I had my Hadamard matrix, I had the submatrices each colored in a different color. what you can do is there's a theorem saying that the discrete Fourier transform of the entries in one of the submatrices must have entries of small magnitude if it's to be a Hadamard matrix, and this can be proven. So what you can do is when the stat solver is filling in the entries of the matrix, eventually it's going to fill in all the entries in one of the submatrices. Then you can take that submatrix, give it to the CAS, have the CAS compute the discrete Fourier transforms entries magnitudes, and if they are too large, you throw it away. You block it because it's never going to extend to a full Hadamard matrix. And this is extremely powerful because almost all submatrices are going to have some entry with a large magnitude, right? Almost every time we give the stat solver finds a potential submatrix and gives it to the CAS, it's almost always going to be discarded. So this was basically, we use other theorems as well. This was one of the main reasons why we're able to go so high, search for Williamson matrices of such a high order. So in conclusion, I really want to stress just how widely applicable this method is, right? Whenever you want to have fast, verifiable, and you want expressive searches, this is a great way to go about it, right? You could write your own search, custom-written search, but you don't want to reinvent the wheel, right? It's very hard to beat a stat solver at search because stat solvers have been engineered for decades to be very fast at search, right? It's very hard to beat them. On the other hand, CASs have also been engineered for decades to be very fast at doing mathematical computations. Why not use both of the tools in the ways they were designed to be used, right? Don't try to shoehorn, some kind of CAS function into SAT, right? You could imagine trying to do a discrete Fourier transform in SAT. It's like, it hurts my head just trying to think of doing something like that, right? You wouldn't want to put a discrete Fourier transform in a SAT encoding, right? It's something which is best suited to do in a computer algebra system or some kind of math library, right? So use both of the tools in the ways that they're meant to be used. And this kind of overcomes one of the downsides of a SAT solver, which is its lack of expressiveness. Okay, so just one slide on the future work, I really do believe that SAT plus CAS methods are forever poised to change what is considered feasible in mathematical search. I've seen it with my own two eyes, right? I come up with some kind of search using either a CAS or a SAT solver, and it's running okay. And then you put the two together in just the right way, and it just takes off like a rocket, right? It really, really performs very much faster than the approaches with just using one of the techniques individually. So I've seen it happen again and again in many different fields. So we really are excited to push this technique to other fields, right? So I am looking for students. Check out my website for research positions, and we want people from different domains as well. The last thing I just wanted to mention is if you are interested in getting involved in this community, one way that you could do this is to go to the SC² workshop, which is happening this year in August. It's going to be online, so no traveling. You can just sign in virtually, and we have a great lineup of speakers. We have 12 talks over the 2 days, and it's a very welcoming community, right? And we're explicitly wanting people from diverse backgrounds, because as I mentioned, if you have that domain expertise in some other domain, it's very likely that these sort of SAT plus CAS techniques can help solve problems in your field as well. So with that, thank everyone for your time, and be happy to take any questions.
Thank you, Curtis. That was a wonderful talk. Moshe already has a question. Please go ahead, Moshe. Umaid, can you unmute Moshe? Or can you make Moshe a panelist so he can... Moshe, can you unmute yourself?
Okay. Yeah, no, I had to be moved to panelist.
Yes.
Very, very nice talk, Curtis. You did not mention that the one TLA you do not mention is SMT.
Right.
It's coming up.
The flavor of an SMT. Can you comment on this as an SMT, as an example of SMT?
It is sort of like an SMT. Yeah, so I get this, a lot of people mention this. One of the differences is that, well, SMT is kind of fixed to a specific theory normally, right? And there's really, I don't believe there's any SMT solvers that support, say, even complex numbers, right? It's definitely not fast Fourier transforms, right? So this is kind of like an extension of the DPLLT framework for SMT solvers.
So let me say it in my own words. So the approach in SMT is usually was to take a complete solver for some theory and then to consider that combination. Instead, CAS is not a complete solver. Okay, it's just a powerful solver for whatever it can do.
Exactly.
And you're still trying to combine it with, you're saying the same idea, let's combine it with SAT. And we don't get a complete solver, but we get a very powerful solver that can handle many pieces of mathematics.
Right, exactly.
That's exactly right.
Okay.
That's how
Very
that's how we positioned the first paper on this, Moshe. Thank you. Any other questions? There is a question from Stephen Gott. So I'm going to read it. Do the verifiable proofs combine both the SAT and CAS reasoning? If so, how do you express the CAS reasoning within DRAT?
Yeah, that's an excellent question. It really depends on what functions you are calling, right? So in the symmetry example case, what we called this library naughty, which tests the isomorphism of two graphs, right? So in the DRAT proof, you have to assume these CAS clauses, right? We just assumed that they were being generated correctly, but then we have a separate verifier, which is going to check the clauses generated correctly. For example, in the naughty case, naughty will provide you, like I mentioned, you have those two graphs which are isomorphic. Naughty will provide you with an explicit labeling of the vertices to show that they are isomorphic. So we had a separate checker which checked the isomorphism of are actually isomorphisms. So we didn't actually have to rely on naughty by itself.
Another question from Yarko Savela. So are you basically using CAS as an extra constraint propagator, or are you doing something else?
You can also use the CAS as a constraint propagator. That was not typically what we were doing. We were using the CAS to generate clauses that we would put in to the SAT solver's clause database.
Cool. So Curtis, I have Massimo has a question. Go ahead, Massimo. Do you have a question, Massimo?
Yes, I do, but I don't know how you realize that because I haven't written anything. Anyway,
you raised your hand, and so I thought.
Oh, okay. So my question is about the communication between the math component and the SAT solver. For example, in the example of the Williamson conjecture, you say that at some point part of the matrix is filled, and then you test the Fourier transform of that part of the matrix. So is something that you do like you have some trigger and callback technology, or you at some point you just stop the search, or you wait the search to complete for a satisfiable assignment? How does it work?
So there's this paradigm that VJ pioneered called programmatic SAT. So internally to the SAT solver, you can call out to using a callback function to any library that you want, right? So as the SAT solver is executing the search, is going to be periodically querying the Fourier transform library.
I just want to add to what Curtis said. So the concept of programmatic search is very similar to DPLLT or CDCLT. The main difference is that we can particularize the SAT solver for specific instances. It's like a non-uniform model of computation. So I can say I have this instance, and I want to make the SAT solver specific to that one instance. Whereas DPLLT or CDCLT is for a class of instances. Another difference is that in CDCLT, the theory part is first order theories, Whereas here, the theory part is, well, arbitrary, and the goal is to provide feedback on the SAT formula. So.
And do you chain these calls, or like you do it interactively? Like, do you buffer these calls? Because I would expect that if you want to stop the solver to call the cast, it's a huge slowdown.
Oh no, it's a callback mechanism. So in many programming languages, you have a callback mechanism that allows you to inject arbitrary code, and you can then compile the solver with your code. So a programmatic SAT solver is like a poor man's CDCLT. By that I mean that try hacking an SMT solver, and you need a couple of PhDs before you can get to that point, right? I mean, anybody. And the point is that with programmatic SAT, the interfaces are so simple. They're very similar, but they're much simpler. The invariants that we impose on them are simpler. So therefore, any user with reasonable programming background can extend the SAT solver for a very particular class of instances, or a single instance if they so wish.
But every time you call the math core, you stop the SAT solver. Somehow they alternate.
Yeah, I mean, you could think of it that way. Yeah. So when you call the math, so there is, when the callback function is being called, indeed the SAT solver, because it's sequential, the SAT solver stops, if you will, and then the callback then feeds back clauses into the solver. And this is what we first proposed in 2015 as part of MathCheck. And then Kurt High took off like a rocket. All right.
Curtis, should I call you Kurt High, or I'm sorry if I'm asking so many questions, but I guess you have very good measures about how much time you spent on one side and the other. I guess you really measure these kind of things. So
yeah, it depends on the problem. Sometimes it'll be more on the SAT side. Sometimes the CAS is more.
Supratik has a question. The problems mentioned in the talk seem to be those which admit a propositional encoding. I presume SAT plus can be used to solve problems that cannot be encoded propositionally using real arithmetic.
Yeah, it depends. And typically you want like a component of the problem encoded directly in SAT. So you might have functions which you can't encode into SAT, but then you call those, make a call to CAS for those.
Okay. Thank you, Curtis, for a fantastic talk.
Thank
so
you.
Clap for everybody else. Oh, Thomas, just if you do this, what Vijay proposed, you could find a drag proof. Oh, go ahead, Thomas.
Oh, yes. Yeah, my question is what you said to find a specific SAT solver for a specific interaction problem with CAS and SAT. And then if you have a specific SAT solver, then solve that, transfer all this to the SAT solver, then I think it should work that then you ultimately have a DRAG proof, don't you?
Yes.
A specific DRAG proof.
Yes.
Oh, yeah.
I think it's an open question we had at the talk, I think when Pavel Pudlak gave his talk, whether it's really possible to encode everything into extended resolution, or if we do need something which is a stronger proof system. I think but I assume it's possible. DRAG would work then. But otherwise, you wouldn't find a SAT solver for that. Right. Do you agree?
I'm not quite following your question. Maybe Curtis.
I think that was mostly, from what I understood.
The question is whether or not a DRAG proof can be generated when you do a SAT plus CAS combination. Is that the question?
Yeah. So we do have DRAG proofs at the end, but like I said, some of the clauses are assumed to be correct, right? They're generated from the CAS, and that has to have a separate reasoning, separately verified.
Cool.
Vaidyanathan has a question. Follow up to Massimo's question. What triggers the callback? Is that the callback author's decision, or is it up to the SAT solver?
So I believe every time you do a unit propagation, right before you're about to choose the next variable, it will trigger the callback.
Right. There are many places, Vaidyanathan, where you can put the callback. One of them is that when BCP is done and it's waiting to either make a decision, you could use that moment to take the partial assignment and check whether it can be extended to a complete assignment. And if it cannot, then the CAS would return a learned clause. Similar to conflict analysis, so we are extending the conflict analysis in some way. You could also extend the propagation method using this. So there are many different points at which you can add the callback. All right. Thank you, Curtis, for a fantastic talk. That was very good. I clap for everybody again. And now it's my great pleasure